Hello students, today we are starting chapter 5, Magnetism and Matter. In first assignment, we'll have 6 questions. The assignment is very easy. First one is compare electric dipole and magnetic dipole. Second one, write characteristics of magnetic field lines. Third one, define magnetic dipole of current carrying loop and a bar magnet. Also define magnetic pole, actually pole strength. Uh, Write unit of magnetic dipole moment and magnetic pole strength. Third question. Compare expression for electric field of an electric dipole at given point with expressions for magnetic field of magnetic dipole. Next one. What is gyromagnetic ratio, also pronounced as gyromagnetic ratio? Derive its expression, obtain its value, and mention its unit. And lastly, we will compare electrostatics and magnetism. So that is the task for the day. Very interesting assignment, very easy one. And if you remember the earlier topics of electric dipole and electric field, there is nothing new. It is there are so many analogy we have between electrostatics and magnetism. So we'll start with electric dipole and magnetic dipole. We know that in case of electric dipole, we have negative charge on one side and positive charge on the other side. And we say that if minus q and plus q are separated by say distance 2a, then there is a quantity defined called dipole moment, and dipole moment is nothing but product of charge and separation of the two. And what is this vector part? Vector is property of dipole moment, and direction of dipole moment is from negative charge to positive charge. Now very similar thing we have in magnetism also. In case of magnetism, we have bar magnet. See, the way we have electric dipole, we have magnetic dipole. Magnetic dipole is nothing but bar magnet. So in case of bar magnet, you have north pole, you have south pole. So you can say that the charges of electrostatics are now replaced by poles. Okay, that is first similarity. Now if I say that the separation of the poles is 2L, or length of the bar magnet is 2L, or length of the magnetic dipole is 2L, then there is similar quantity called dipole moment be defined for bar magnet also, which is nothing but M, which is equal to small m into 2L. Okay, so what is Q? Q is charge. What is M? M is pole strength. Because different charges have different electric lines coming out of it. Similarly, different poles have different magnetic field lines coming out of it. How do we describe electric field of electric dipole? So we say that in case of electric dipole, uh, we have field lines coming out from positive charge and field lines enter into negative charge. So I can describe electric dipole like this. This is how we describe electric field of electric dipole. Now very similarly, if you consider magnetic dipole, that is bar magnet, you have north pole and south pole. So in case of bar magnet, you have magnetic field lines coming out from north pole. So the way we find out electric field of electric dipole, we can find out magnetic field of magnetic dipole. Now there is one very essential difference here between electric dipole and magnetic dipole is, in case of electric dipole, Even along the line joining the two charges, electric field is from positive to negative. Whereas in case of magnetic dipole, that is bar magnet, we know that inside the dipole field lines go from south pole to north pole. Okay, this is how field lines go inside the bar magnet, and hence the essential difference between electric field and magnetic field is magnetic field lines form closed loop. See, magnetic field lines, this is how they form closed loop. So that is very essential and basic difference between electrostatics and magnetic field. Electric field lines of stationary charges don't form closed loop, but magnetic field lines do form closed loop. They start from north pole, they enter into south pole. Otherwise, the way we have characteristics of electric field line, that if you draw tangent at given point, you get direction of electric field. Here also, if you draw tangent at given point, you get direction of magnetic field. The way you have uh, density of field lines indicating field strength, like if you compare these two fields, say E1 and E2, E1 is greater than E2 because field lines are close, and E1 is uniform, E2 is also uniform, but E1 is stronger. Similarly, in magnetism also, we can say that if field lines are equidistant and parallel, then it is indicating uniform magnetic field. See, if you consider these two magnetic fields, magnetic field is normally defined, symbolized by B. So B1 is greater than B2. So there are similarities between electric dipole and magnetic dipole. And this is a very essential quantity, magnetic dipole moment. What should be the unit of magnetic dipole moment? Okay, I'm not mentioning it for now. We already have magnetic dipole moment defined for a loop. So let us go to that part also. We know that any current carrying loop, suppose you have n turns, and if it is carrying current I, then magnetic dipole moment of current carrying loop can be defined as NIA. Now, see, electric dipole is giving us electric field, magnetic dipole is giving us magnetic field, but in case of magnetic dipole, you have two options. Which are the two options? Options are, you can produce magnetic field using bar magnet, you can produce magnetic field using current carrying loop. Now here also, the field lines are very similar. Field lines come out from one part of the loop and enter into the other part. So the situation is very similar, and so I can say that this current carrying loop is also having bar magnet inside it. You can consider one part as north pole and other part as south pole. So if I want to produce magnetic field of 2 Tesla, I have two options. I can produce it using coil, or I can produce it using bar magnet. So if I compare NIA with M into 2L, I can say that M is NIA by 2L, but N by 2L, that is number per unit length, as a separate symbol. Okay, so this is how you can define pole strength of a magnet. What should be its unit? See, A is meter square, and this is number per meter, and I is ampere. So what should be the unit of pole strength? It should be ampere meter. Okay, so ampere meter is the unit of pole strength. And what should be the unit of dipole moment? We can find out using this formula. You are multiplying current with area, so it should be ampere meter square. And what is the direction of magnetic dipole moment? In case of bar magnet, it is from south pole to north pole. In case of electric dipole, it is from negative charge to positive charge. In case of magnetic dipole moment, it is from south pole to north pole. And in case of loop, you can use right hand screw rule and determine direction of magnetic field. So that is what we should be knowing about magnetism at this point of time. And then the way we have electric field of electric dipole, we have magnetic field of magnetic dipole. How do we explain electric field on axis of dipole? Suppose I have a dipole, say negative charge and positive charge, and I want to find out its electric field at some distance, say z. So let the length be 2a. Then we know that the electric field on the axis can be given as 1 by 4 pi epsilon 0 p into 2z upon z square minus a square whole square. Similarly, if you have bar magnet, and suppose in case of bar magnet, if you want to find out its magnetic field at some point, let's say z distance on its line, let the length of the bar magnet be 2L, then the magnetic field can be given as B is equal to mu 0 by 4 pi. Now see, this is another very important difference between electrostatic and magnetism. In case of electrostatic, the constant term which very frequently appears is 1 by 4 pi epsilon 0, whereas in case of magnetism, the term constant term is mu 0 by 4 pi. Okay, now instead of this P, what do we have in magnetism? So we have dipole moment, capital M, distance remains same 2z, z square minus a square raised to 2. Now instead of a square, I should take L square, so I'll mention L here. Okay. In case of electric dipole, if we have Z very greater than A, then we say that electric field is 1 by 4 pi epsilon 0 2 P by Z cube. Similarly, in case of magnetism also, if you consider Z to be very greater than L, if the point is far enough, then the magnetic field can be given as mu 0 by 4 pi M by Z cube. So the way electric field has distance dependence with 1 by r cube, magnetic field is also having similar relation with distance as far as magnetic field on axis is concerned. What about the equator? In equator also, the formula is very similar. I'm not mentioning it, we'll see it in answer. But we have very similar analogy for electric field and magnetic field at some point on equator also. Now, if I consider the electronic motion, now see, we know that electrons are orbiting around nucleus. So if I consider some electron to be moving in orbit, it should have its own dipole moment. So I can say that dipole moment of the electron is nothing but I into A. Okay. How much is the current? Current is charge of electron upon time of revolution. So Q by T, here I have AT, and area is pi r square. I consider the radius to be r. Now what if I define angular momentum of the electron? I hope you remember angular momentum is nothing but mvr. So m is mass of electron. Let me mention it as me because m is used for pole strength also. So how do we define velocity of the electron? So it is me distance upon time, that is 2 pi r by t into r. So I have 2 pi by t me r square. This is the angular momentum. What if we take ratio of this two? Let us take ratio of m by L. M by L will give me E by T into pi r square upon 2 pi by T into m e r square. How many terms will get cancelled out? So we have r square being cancelled out, 1 by t will also be cancelled out, and pi will also be cancelled out. And what we will be left with? We will be left with e by 2me. What does it mean? This is very important result in case of magnetism. See, what this result indicates is that if you take the ratio of magnetic dipole moment and angular momentum of an electron, the ratio is constant. Why it is important? It is important because suppose if you subject this electron to any external magnetic field, suppose I applied magnetic field. Now we know that charges experience force F is equal to QVB. So electronic motion will be modified. So current will be modified, magnetic dipole moment will be modified, and if speed is changed, then MVR may also be changed. But look at the ratio of these two. Ratio will not be changed. The ratio remains constant. This ratio is called gyromagnetic ratio. Okay, you can substitute value of E and ME, that is mass of electron, and find out its value. So that is all for today's assignment. Let us have a quick look at all the answers, starting with the first one. I'll very quickly go through the points and I'll touch upon important points only. First one is comparison between electric dipole and magnetic dipole. So what is electric dipole? It is system of two equal and opposite charges separated by some distance. What should be magnetic dipole? It is system of two opposite magnetic poles of same pole strength. See, in case of electric dipole, we have same value of charge, magnitude of charge is same. Similarly, in case of magnetic dipole, pole strength is same. Normally, the symbol of distance in electric dipole is 2a, whereas in case of magnetic dipole, it is 2l. What is this arrow indicating? It is showing direction of dipole moment, which is from negative charge to positive charge for electric dipole and south pole to north pole for magnetic dipole. As mentioned earlier, this is electric dipole moment P. Here is magnetic dipole moment capital M. And what is small m here? It is pole strength. The direction of electric dipole moment is from negative charge to positive charge. Direction of magnetic dipole is from south pole to north pole. Electric dipole moment is expressed in terms of coulomb meter, whereas for magnetic dipole moment you have two units, ampere per meter or joule Tesla. Electric field lines come out from positive charge and enter into negative charge. Magnetic field lines come out from north pole and enter into south pole. But this is the difference. Along the line joining the two, along the line joining the dipole, field line is from positive to negative, whereas inside the magnetic dipole, field is from south to north pole. That is the difference between these two, and that is the last point. Second question, write characteristics of magnetic field lines. Now, I'll not read this answer because it is very similar to what we had in electrostatics. Field lines of stationary charge don't form closed loop, whereas field lines for magnetic poles, they do form closed loop. That is the difference. Otherwise, the points are very similar. You can go through the points. Third one, define magnetic dipole moment of current carrying loop. Now we know that for current carrying loop, magnetic dipole moment is NIA. Earlier also we had, and then for bar magnet, it is pole strength into 2L. Now be careful, 2L is the distance between the two poles. It is not double of the distance, just like electric dipole moment. And now, if I have a loop and bar magnet producing similar field, I can compare the dipole moment of these two, and then we have m into 2L is equal to NIA. Make M subject of formula, and this is what you get. So we can say that pole strength is nothing but Nia, where N is number of turns per unit length if you are measuring in terms of loop or solenoid. And what is the unit of pole strength? Unit of pole strength is ampere into meter. Very important quantity from numerical point of view and exam point of view. Lastly, next is electric field and magnetic field of the dipoles. So again, we are starting with the electric dipole moment and magnetic dipole moment, which we saw just now. This is the electric field on axis at some point on its axis. Compare the two. See, one difference is in constant term. Constant term is 1 by 4 pi epsilon 0. Here it is mu 0 by 4 pi. Second difference is instead of electric dipole moment, you have magnetic dipole moment. Rest of the things are same. This electric field is in the direction of P, whereas magnetic field is in the direction of M. And as mentioned earlier, for large value of Z, E is proportional to R cube. For large value of Z, B is proportional to R cube. And a very similar thing we have in equatorial field also. See, equatorial field of electric dipole can be given as P upon y square plus a square raised to 3 by 2 with constant term. And very similarly, we have magnetic field at some point on its equator. And again, this relation holds true even for equatorial field also. And what this negative sign indicates? It indicates that the direction of magnetic field is opposite to the direction of magnetic dipole moment. So these are the points of comparison of magnetic field of magnetic dipole and electric field of electric dipole. Then gyromagnetic ratio. What is gyromagnetic ratio? It is ratio of M by L. What is M? Magnetic dipole moment. L is angular momentum. So angular momentum is mvr, with distance upon time, and this is the expression for angular momentum. Magnetic dipole moment is Nia, but in case of electron, you don't have. If you write Nia, in case of electron, N makes no sense, so simply it is I into A. What is I? Current. So current current is charge by time. Negative sign because we are talking about negative charge, and this is what we get. Take ratio and you have E by 2m with negative sign, and this is the value. Might be asked in MCQ. This is gyromagnetic ratio. This ratio is known as gyromagnetic ratio. And lastly, we have comparison of electrostatics and magnetism. If you remember the equations of electrostatic, it is very easy to remember equations in magnetism. Look at the comparison. Constant term which often appear in electrostatic is 1 by 4 pi epsilon 0. In magnetism, it is mu 0 by 4 pi. Whatever is the role of charge, it produces electric field, electric force. Here, poles are producing magnetic field lines. So poles are taking a role of charge. Electric dipole moment P is Q into 2a. Magnetic dipole moment is pole strength into distance. These are the formula. It would be easier for you if you keep this comparison in mind. You will be able to remember both sets of equation. Field on equator, at large distance. Yes, this is another thing. Electric force is F, which is charge into electric field. Similarly, magnetic force can be defined as pole strength into magnetic field. Now, there is one difference. You can have single positive charge, but you cannot have single north pole. You cannot have single south pole. So most of the time, this equation is theoretically, it does make some sense, but practically you always have north pole and south pole together. So that is another difference between electrostatics and magnetism. In case of electrostatic, you can separate positive and negative charges, but in magnetism, you cannot separate north pole and south pole. We used to express torque for electric dipole as P cross E. Similarly, we will have torque on magnetic dipole as M cross P. If potential energy of electric dipole is minus P dot E, potential energy of magnetic dipole will be minus M dot B. If you oscillate electric dipole in electric field, this is frequency of oscillation, and similar equation we have for magnetic dipole, frequency of magnetic dipole. Im is moment of inertia. Here also Im is moment of inertia. So that is all for this assignment. Very easy thing, but you will need practice of all these equations. So do write all these answers on your own. Thank you.